Okay, so okay, we'll go to second part of the workshop. So okay, so first, we finished with this slicing part. So like just cutting geometry in two. So now we're gonna do it in a bit more precise way. Like I guess quite a few of you know about this Gooch shader kinda, which kinda cuts some geometry in two. So I'll show different methods to do it, and then we'll try to do a geometry version. So the first method to do is when we do the clip plane, so which is exactly this Gooch shader, but this time we don't want it with the center of triangle. We really want like a plane which properly, accurately slices the geometry. So the first time is like here I got just my sphere with normals, and what we want to do is we want to have this geometry with a sliced version. So we have a plane, and if you're one side of a plane. But if we looked at previous version, like in previous version, we were doing it. We were like you can see the little cracks here. Mouse again. Show cursor. If we look around here, we can see these little cracks because because we base ourselves on the center, and if the center is on one side, we get rid of the whole triangle. So we can't really achieve this like smooth surface version. So the first one that people tend to do normally is you will do it in pixel shader. So you're allowed to do a discard or clip, which is exactly the same thing. So, well, clip plane Gooch shader is reasonably easy. It's like you have your clip plane value here, which is just float 4 as usual. And then you will do the distance, sign distance to plane, which is this dot product one. So it's been the most widely used, I guess, but well, this one has a really serious problem first. It doesn't support anti-alias. So if we really zoomed, if I change my multi-sampling to 4 instead of 1, it's still aliased because discard and clip block aliasing. So there's a much, also, while you've been writing pixel shaders, there's a much easier version. You can just use a clip plane in vertex shader. So you have this here on your vertex shader, you say this is my clip plane, and you just set clip plane's attribute. So that also works. So instead of even writing the equations yourself, it's already available for you as keyword. So you don't have to do it manually. The pipeline quite does it for you. And now if you change the multi-sampling, you can see, and I want again, you can see the difference, like you have anti-aliased edges, obviously. No, it's okay. So now there's a third way, like this, you have a third way, you can also, like the problem is with that one, because everyone has a little of an issue. So first, doesn't support anti-alias. Problem with attribute, it will only be on SV position. So you can't really tell which attribute you want to use for discarding the pixel before it reaches it. So instead, you can use clip distance, which is doing exactly the same thing. So but instead it's output of vertex shader. So you have SV clip distance output of vertex. So what it will do is when you interpolate the triangle, it will interpolate the clip distance, and it will also block pixel shader depending on this value. So you can do pixel accurate clipping with using this instead. And using this method, it also supports anti-alias, which, well, if you need anti-alias, you can't really use clips. So this method is working, and you're allowed 2 clip distance. So if you want to do a second plane, you can do SV clip distance 0 and SV clip distance 2, 1. No, it's not like this. Ah, oops, sorry. Yes, okay. So, and we need second clip distance. So my clip plane 2, clip distance 2. And now if we change that one, now we can do 2 planes in one go with just with vertex shader. So it's also anti-aliased. You can see, like if I go here, if I go to, yeah, so that's like no one sample per pixel, and if I go to 8, you can see edges. Yes, of course. So I like the small difference between the discard clip and the, here you provide the distance, so you don't provide a plane equation. You just provide an arbitrary distance, basically. So you need to you still need to perform the dot product for the plane, and you output SV0 and SV1 as the distance. You're not supposed to only use a dot equation. You can do clipping on Z, for example. You can use anything which will give a distance, will work, basically. So that's the one here. But the problem with all those 3 methods is it all operates quite on pixel shader. Like the clip distance only works if you go to pixel shader. Clip distance doesn't work with stream output. So that means if you want to reuse the geometry, you can't. You have to perform this clipping everywhere. So since we've seen stream out this morning and see we can perform like already this selection, we should, like I'll show how you do it in geometry level. So the problem is with clipping a triangle, if you do it at geometry level, is you have like 4 cases. So you have your triangle will be on one side of the plane completely. Your triangle will be on the wrong side of the plane completely. So if it's up completely, you want to push. If you just want to slice, you want to push one triangle, the whole triangle itself. If it's completely under, you just don't push anything, you just ignore it. But then you have the case 1 point of the triangle is below and 1 point is above. In which case you will need to push 2 triangles. And you have the obviously opposite case. If 2 are below and 1 is above, you will need to only push the cut triangle. So I can do it with a fantastic tool called Paint, which will be the best one for explaining this. So we have our plane here. And I'll do it a 2D version, but 3D is 100% the same. So now I got my triangle. Oh, I don't know how to use Paint, so sorry if I'm a bit slow.
I see.
So now we have this and this. So you have the case number 1 where triangle is completely above. So in that case, we will need to push. It's quite really straightforward in that case because you just append the triangle done. There's no complicated problem. With the second case, you have the opposite case. You don't push it, so it's even easier. You just do nothing. But you have the case which is this one, and the case which is this one, which is the exact opposite. Yeah, and no, I don't want to move this line. Ah, okay. Did not new Paint that hard. Okay, so second case, we can see you always output. Let's say we want to keep I need pencil tool now. Let's see, we want to keep that part only on top. So the first case will start by this one. You only have one triangle, so you need to append a smaller triangle which just goes through here. So you want to append only this little blue one here. And the other case is you need to append this whole area here. And this whole area, luckily, is some form of parallelepiped, and which can be represented as two triangles. So which gives us like some, either this one or either this one, it doesn't matter. So let's say this one. So now we need to push one triangle which goes from here to here and one triangle which goes from here to here. So now, actually, because we're already doing clip planes, we kind of have half of the solution, because we already do calculating the distance from the triangle to the plane. So that means by knowing the distance, because we need to know the intersection point, but because we know the distance between this point and the plane, we can calculate it easily. Then we can calculate this intersection because we just add the direction of the edge and we multiply by distance. So it's very straightforward to just calculate this with simple equation. So instead we're doing this geometry version. Okay, save all, which will be GS version. So it's a GS version which goes directly, that one doesn't do stream out, but since it's a geometry shader, you can push it to stream out just copying the files pretty much. So idea is, I'm drawing the sphere at the same time, so we can use rasterizer and make that one a little. So we're just drawing this circle on top. Is my mouse again? But the difference is now if I put wireframe, I'll just get rid of this one actually. Now if we put wireframe, now we can see the difference. So now it's not done in pixel shader anyway, it's done at the geometric level, which means now we can reuse that geometry completely. You can send to a stream out, you can send the other side, so you can repeat it, so you can do stream out 10 times, for example, and just cut several parts. So idea is not to so the idea is we have distance to plane, which is and we can do a ray to plane. So ray to plane is pretty much the same. We have direction. If our direction is really low for some reason, it's a specific case, we just say we don't hit. Then we do this distance dot which is exactly the same, and that gives us the distance from the plane. And if it's less than 0, we say we don't hit, otherwise we hit. And the distance gives us, so we tell if we hit the ray or not. So what we do is we take every 3 triangles and we calculate the plane distance to it. Then we have to say how many elements are on one side of this plane. So we put it all in a like called sides, and we do a plus. So that means count will give us the number of triangle on one side. So now we can get our 4 cases, which are here. And last case is not here because it's the one where you do nothing. So but normally we should have something like here. If count equals 0, here and do nothing. So this first case is really straightforward. You just push yourself. The second case is you have only two, so we still need to, we don't know which one is yet around there. So we say this is the index of the one which is below, so we need to find, we know we have two, so we need to find. And we grab the other one, other two. Now we can, so now we take the edge, we take this point, we know the directions, so you send a ray through this direction, which will give you, so this is, we have the normalized direction, so we take the other edge, so we say, take this, we want to check from this point, so we take this point, that we subtract to calculate direction, and we cast a ray starting from here to this plane, which gives us, we already know it's gonna intersect, so we can simplify, like the ray equation is normally more complicated, but here, since we already did the triangle check, we already know that the intersection will happen, so we can completely get rid of the part where it's not gonna happen. So that gives us the distance, and the projection of the distance gives us this point, which we need to repeat to do it from this version. So from this point we calculate the inverse version, which brings us this, and from this we can build our quad, which is a standard quad strip. Then if case is 1, we exactly do the same operation, so but we cast from the other side. So we only have to push one triangle, which is even easier. So we check, we do it from this one, we just cast one from here, and that gives us the 0, 1, 2 triangle to do.
How do you determine from which vertex to cast the ray?
Because I know here which ones are above.
Okay.
Like here I need to check which one is above. I know there's only one, so I just do a quick check if it's X, Y, or Z.
But performance-wise, these triple expressions are the same if?
That should be compiled same-ish, yes. That should be compiled the same, yes. I mean, I can't really check, but normally those, if it's a really simple if, it will likely be the same. And so, yeah, so that means now we have the slicing. Well, I'll do the stream out version, because it should be quite quick. Here, and let's just copy here. Which one's the best? Okay, and here I push. Yeah, but here I go to the plane. So, well, I think, well, actually, you can pretty much take this GS and put it in a stream out pipeline. So, actually, I should not have taken that one. Though. That one will be nicer. So now if we take back our multi-stream example, which was properly slicing the two geometry, we're going to replace the mini clip by the more complicated version. So I'm not going to rewrite it by hand. So. And plane. Okay, so here. Okay, so we don't want the color. And we don't need the multiplies anymore, because in that case we don't want to re-render in screen space. So generally porting GS from stream out is just about that. You need to add the stream out definition, and you need to also make sure you don't use all the camera projection transformation, because you still want to keep your object in normal space. So all this GS, it's very easy to prototype because you can write them directly as a texture render. They're really easy to change something to try if it's working. And then once they're working, it's quite also easy to bring them in their own little system.
You've got a semicolon.
Yeah, but I still need to get one more null too. Yeah. And get rid of well. Up.
Yeah, the semicolon there. Oh, well, that's one way to get rid of it.
Oh, no. I need normal also. Let's get rid of it for now. That will do. Okay, and we have just normal here. Plus 3. Oops.
Sorry. Sorry about the drama.
And it's quite complaining. Ah.
Sick, bro.
Yeah, so and now you can see we can, well, now we have our properly cut geometry, but we can completely reuse it several times. So I keep it for you as exercise to do the split version, so to output from each side. But yeah, it's too well, geometry shader, you can do quite complicated things, so you can really do some serious decision on what you want to exactly do. It's really flexible. And because this one also, you still use triangle, obviously anti-alias works natively because you just split your model. If you want, you can export it too, so you can do a bit. As soon as it doesn't go to pixel, it's much easier to work with because it's still geometry. So we're gonna, after geometry, we're gonna do more. So after stream out, well, there's we've seen there was quite geometry shader stage quite a bit more in depth. So now there's another stage which is tessellation. So we're gonna do a bit of tessellation.
Sorry, can I just ask quickly
Yes.
before you move on? The plane intersection,
Yep.
if I change it to SD sphere, I have to also find a ray to sphere function? Or
Ray to sphere is quite straightforward,
right.
but the problem with sphere is it's not a plane. So instead, if I take back Mr. Paint, and I do another line here,
There'd be a lot more possibilities for how the triangles get put up.
you
Right.
if in that case instead you get something like that. Well, actually, yes, you get something like this. So if you take your triangle here, okay, line, 1, 2, yes, 3. You don't have a line anymore, so that means that's not really a triangle. That's the problem. If you start to use spheres, then you need to kind of decide of a resolution to generate the arc here. So with anything which is like with a cube, you should be able to do some form of something. You'd have some specific cases as well. But for cube, you can do 6 planes too, of course. So you can, of course, repeat it as soon as you have it as trim out. You can say, I'm doing it once, but you can cut to another plane again. So you can repeat as much as you want. So you can do complex shapes by just using planes all the time.
So you would recommend more to do multiple planes? For example, a cheap box function is better to use 6 planes?
The advantage of several passes is every time you do a new pass, you've been removing things because you're cutting something. So that means the first pass you have the whole sphere, but the second pass you will never have more than the whole sphere, but you will have only less. So that means the second pass you might process half the data instead.
Yeah.
So it's a trade between doing several passes, but every pass you process less and less data. So every new pass is generally faster, except case where something passes the test all the time, in which case, of course, you do it 6 times 100%. So I'm not sure which one I want to use to start. Okay, I guess I'll do first the quad one. No, I'll do the line one because the line one makes a bit more sense up front. So idea with tessellation, now we're gonna actually do 2 modes of tessellation. We're gonna do tessellation with, there's tessellation with vertex, and we'll use tessellation with domain shader. You don't need to use tessellation all the time to tessellate something. You can do it in vertex shader. In some cases, it can be quite faster. And so to do that, we just actually gonna redo this segment node because it's quite a good candidate. Like one problem with segment, I'll try to explain it actually by not showing this example. I'll have to start one. Well, well, it's not connected, so perfect. So the problem with segment is, for example, if I do a constant again, and if I do random spread, okay, I'm just gonna do 300 for now, and we say well, it's just, anyway, it's just segment, but now we want to say we want more with this inner radius, we want more with these cycles, we want some like this, well, and we want some, oh, please again, 2D. And we want one as like this and one like this. So we want different, we want everything a bit dynamic, basically. Let's just summarize it. So problem is, well, we can send a big spread of parameter in the segment, but what the segment node is gonna do, it's gonna rebuild the geometry in CPU every frame with the new parameters. So if I start to say I take a random spread of like, well, let's just say 50 will already, and per meter. Okay, so now we are at 120, but now if we start to animate the random spread and start to change, so we're still 120, but if I start to change resolution a bit, well, okay, it's quite good machine, so it's gonna take its time to, okay, 200. Okay, so if we have 200 of them, like completely different, if we have 200, our frame rate starts to suffer quite a lot. And so, but we want, well, let's say thousands or 5,000. So problem is, well, obviously we just seen that doing it on segment is not up to the task, so we're gonna do it with tessellation instead. So the idea with segment is actually you have this pin which is phase, which is how much, it's a bit of rotation basically, it's just a rotation. Then you have the inner radius, then we have cycles, and that's for texture coordinate, but let's say for now we'll ignore that pin. And we have the resolution, so because sometimes if we put a resolution of 3, it can look like a triangle or it can look like an hexagon, so it's a quite really flexible node to do various type of shapes actually. So now the first thing is we have those 4 parameters. So the idea is we should send those 4 parameters to the graphics card and just deal with it in shader. So the first version will not be, the first thing, like segment is just a part of an arc of a circle, basically. If we want to think about it, the first thing, it's just the first part of a circle. So we're just not gonna think about the thickness, we're just gonna think about the shape. It's just a simple circular path. So to build it from scratch, that's the resolution of our segment, and in the shader we pass the same parameters as what we will do in the segment node. So instead also of sending this big geometry, it's gonna be all done on the fly. So the first part is, yeah, we're gonna want to really do it in 2 steps. So the first part is really to build the path of line. And then from the path of line, we're gonna have line geometry. In geometry shader, we can take this mini segment and build a little thickness quad out of it because it's really easy to do in geometry shader. So we can easily split the case into, say, first we build the line path, and second we will deal with the extrusion. So the first thing is to build the path. So here we go. Now we have a 7. We have our resolution here, and I'll just put perf meter as. So we have our resolution. And now if I put my random spread in outer radius, well, they're all in the same place. Yeah, but now we quite happily stay at 120. We can try to push more objects. So instead of 200, I said I wanted 1,000. So let's put 2,000 then.
Yeah.
And still with 2,000, so we have like 20 times more object, but we still quite double the frame rate. So that, well, that means we're on quite good path. So we're rebuilding every frame. We're not caching any of the geometry because we need to animate it anyway. So by the time we need to animate something, we need to reform it. But this one is doing 100, so it's building one call per segment. So we'll see first how it works. So idea is we send this null geometry and we said we want line. So I explained line strip is a pass. So obviously we say we want to draw 4 vertex and we want them to be a pass. If we want it higher, we can suddenly say higher. So, and yeah, if I increase the resolution, it still doesn't complain. Like if I put really high res on other one. So the first thing is, so we'll just do null geometry. So we have this vertex ID, but no, actually it's even easier than this building this grid because we can think in one dimension. Like we just have vertex ID will be a number between 0 and 7. We know we have a path of 7, so we can already know the texture coordinate, which is our number, and then we just apply a circle, so cos sine, and we add the cycles and the phase. So the cycles is a multiply for the whole revolution, and the phase is an offset, basically. So the phase is the starting point angle of the circle. If we change the, well, it's not really visible with those resolution, but if I take another LFO here, yeah, phase will just be a rotation. I'll try to do it a bit slower still, because it's a bit fast. So phase is just the initial starting point, so it's just an addition when you think in polar coordinate. And well, then we multiply to screen space and we're pretty done. So we've just drawn our circle, but for the moment we don't have this thickness parameter, and when using segments, the most, well, that's quite what makes it really interesting, is to be able to say, for example, you want 3 or 4 elements. Well, things like that, for example. Generally, what we want to design is things a bit that way. And uniform scale. I'll just do it by hand, but yeah, but it's generally the type of graphics people try to achieve with segments. So, well, this form of old shades are quite common and pretty popular sometimes. So the idea is to do well, but yeah, you can see even smaller one. If you want to do this repeat, you can get easily 16 or 30 of them. So if you need to have quite a lot of the screen, it might grow quite, you will need to build a lot of segments, so to have good performance on generating them makes quite sense. So now we have done with our line pass, which was quite straightforward. Of course, you can spread the resolution here. So you can say half is now circle and half is triangle. Or, well, anyone, you can define individual segment one by one if you want by hand or using random spread, using whatever you need. But now, well, what we said is the idea is we need to still build this mini tape part. So normally building this tape part is a bit tricky doing this type of thing, but because we already know that our segment is a circle, it makes it quite much easier. So that's going to the second one, which, well, is a segment again, just a one version in geometry, and I'll do, no, it's wrong. Yeah, so basically that's this is the same shader with the geometry shader on top, which adds inner radius, so we can, well, we can finish that proper shape. So now it's exactly rendering what we need, but first, the idea was to really show that line. And now we have that line. We receive that line in geometry shader. Here, so we receive it as a line because we asked for a line strip. So the geometry shader, instead of receiving a triangle, in that case it's receiving a line. And then we still want to output triangle stream because we output two triangles. We output the mini parallelepiped, basically. So first is, well, since we have a circle, it's actually really easy because we need this one. Here. We have the center of the triangle. If my center is 0 here, we can clearly see it because it's 0. And we know the exact point where our element is. So what we need is we just need to use the inner radius to find where is the second point. So if I zoom again here, so we start with a line which is this path, the outer version we've built first. And now we're going to start to bring one part inner and build 2 quads to build that thickness. So it's actually all, again, really straightforward. It's like you get your 2 position, and now this one is just like a multiplied by the radius because you go from a 0 to 1 length, so you just have to multiply. There's no more complicated part. This one I'm not using stream out, so we're still pushing to the screen space standard transformation. And we output our quad, so 0, 1, 2, and 1, 2, 3. So we just output our quad strip. And so we have our built-in segment, which now we can like push a little bit more. So that one is going to outer here, and that one is going to here. So let's put 2000 transform. And no, that will be 1000 of them, and we still have 2000 of them, which are still all and yeah. Well, it's just, anyway, it looks a bit like soup because there's a bit too many. Well, okay, but now we have a bit more of a field of them, so it looks a bit better. So yeah, we still have quite complete ton of them, but frame rate is still not. But yeah, instead, well, I'm still running at 100. So compared to 100, which were built dynamically and we are running at 60, now we have 2000, which runs at 100, which, well, makes quite a decent difference. And I think I'm on debug device build, so that's probably even faster normally. So that's the first part. So instead we tessellated, kind of tessellated in Vertex, and we did apply the extrusion in geometry shader. And so we already have this part. Now what we'd like actually is to be able to, for the moment we're doing one draw call for all of them. Like, so we have just standard spread. Now we'd like to instance them. So instead we want to send one draw call saying, give me, here I'm saying 1000 times, draw me this segment, then this segment, well, which doesn't exist yet. Now what we want to do is we want to batch. So we'll say, for example, I want 2000 segments, deal with it. And we obviously have all the properties that we can modify. So we move to the batched version, which is pretty much the same as anytime doing instancing. So you take every parameter you need as some form of array, and you put them in dynamic buffers. And instead of sending my geometry like n times, this time I want to say my vertex count is my resolution. So that means I want segment of resolution 7. And instance count is I want, well, here 8 of them. So the small difference is attributes. Now we can't send them as input. We need to put them in a buffer. So we have here. So in that case, I get a little lazy because I have only 4 attributes: outer, inner, phase, and cycles. I just use a vector 4 dynamic buffer because I'm lazy to build my own, but I'll have to build it later. So for now, we just use a float 4, and we say X is outer, Y is inner, phase is Z, and W is cycles. That's it. We just give a meaning. It's not too But what you can do is actually in the shader, you can create a struct like this, so CB segment data, which has 4 float. And you can create a structured buffer of this because it's 4 float here, and float 4 is anyway the same thing. It will be interpreted the same way, so you don't have to think about this X, Y, Z inside the shader. You can still build a struct that matches. So because it's a bit more convenient to work with the real property name, working with X, Y, Z makes no, well, when you come back to it 1 month later, you forgot.
I'm sorry, I have a question about dynamic buffers. Since a while there are different preferred buffer types.
I'll just finish that section and then I can explain that, okay? That will be a bit different topic, but I think it's useful. So let's just quick finish that one. So we have our structured buffer on segment. So now we still send nothing to the card. We don't build anything in CPU, which is one of the really nice things. We just have a vertex ID and an instance ID. So we just have 2 numbers, which says I am segment number 0, and this is my ID. So we just generate 2 numbers instead of this huge amount of memory. And we can really, because it's really small calculations, the graphics card is really designed to do this thing fast. So it's really, it's probably more efficient than even building and caching the segment. That's when we move to next stage after. But so for first stage, so we have pretty much the same. I keep world as float 4. So we go through vertex, we do this, and we do a modulo because we need to eventually have 1 buffer with 51. So it does slice-wise like you work with a spread. So you do a modulo on the accessor. It's just, spread is just that. It's just an array that you access that way. That's it. It's just you have this cyclic access, like you would use a sampler with wrap. It's the same concept. So now we have, well, I just use world position, so it's just a translation vector because I was lazy. And I pass inner radius because you need it for the taping. So now you have your line. You can, well, you build pretty much the exact same, and you build it as a sprite. It's like self-align. If you look in the sprite shader, we make sure that the quad we multiply it by the inverse view, so we always rotate it to face the camera. That's what that we do with particle on sprite all the time. You have to multiply by inverse, like this is view. So if you have your view is an affine transformation, there's no scaling. So that means you can basically use the inverse of this part, and this will be the rotation. So that's a rotation matrix. Actually, you could use a transpose as well in that case because transpose is inverse, but normally people tend to just do inverse. So you multiply the point by the inverse of the rotation. So all 4 points face the are aligned in one way from the camera, and then you translate them again. So you cancel the rotation of the camera and you translate them. So that's how we do the self-aligned and so now you have, like exactly as said, we have this so plenty of segments which we can instance a lot, but the only problem now with instancing is we can't really change this vertex count anymore. This vertex count is not spreadable, because if you spread this vertex count, that means it's like a multiplication basically. So it's like you will render, if you have 2000 here and you have 2, 5 and 32, and let's actually this one even still works per meter. So this one does everything in one call, but has this issue: we can't really spread individually the resolution, because the vertex shader you have to tell how many inputs you need, so you can't really decide on the factor dynamically in the card, which is quite annoying because we really went a step back from our previous design where we could have a mix of triangles, hexagons, and all various shapes. Now we can only have one type, which is quite boring. So that's when we will have tessellation entering. But first I'll answer the question of buffer. So dynamic buffer has 3 types of buffer type, indeed. That's true, they did not got extremely documented. Let's do list. So basically it's really summarize how they uploaded to the card. So it's depending on how you will use your buffer, one might be more efficient than other. It's just optimization. It's a bit optimization. So basically dynamic means generally you will write once and read once. In that case dynamic is the best because dynamics offers the fastest upload to the card, but will have the slowest read on the card. So if you plan to use your data not much but very frequently, then dynamic is the best choice. Like constant buffer, which are hidden on the variable, are always dynamic because they're this very fire and forget type of buffer. But for dynamic, so default is creating them as non-writable, and then we have to do another version of pushing. So if you do a write once per frame, but read it several times in the frame, or like read it a lot within loops, then in that case, default is the best choice. And immutable basically just destroys the buffer and creates a new one every time. Every time you have apply here, it just like kills the old one and just replace it by a new one. It's like immutable. It's like you don't I can't change data, so the only way to do that is to just remove one and make a new one. So if you have static data, obviously you use immutable. So you have an unopen standard unopen pipeline. You set up data you need, and you just remove apply after, and you will have the best read on immutable and default should be same-ish read performance still.
So sorry, what's the difference between this and just having dynamic buffer with unopen if I want to apply only once?
Yeah, you do exactly that. You do immutable and put an unopen on this apply pin, and you're done. That's it. Yeah, the advantage of immutable in that case, it doesn't reflect, but is you can upload them in background as well. So you can do background resource upload, but only with immutable. So now we've done our batch part, but we've seen we've been losing the resolution. So now we need to, so vertex shader is not so useful anymore because we still really want to keep this dynamic resolution. So we're gonna do a version with tessellation has an option. At some point you have to set the tessellation factor. So basically this tessellation factor is exactly the missing piece of the puzzle, which is we want to say the resolution, but somehow reading it from a buffer before to setting it before the draw. So we need it while the shader is running, we need to be able to read it somewhere. So to first do the tessellation, we have to set up we have to change a little bit the way we're setting data. So I'm doing a non-batched version first. So it's a bit easier to spread elements, and then we can go through another one. So that's lucky. So if you're on ATI, this patch will crash, by the way. Just to tell you. Unless I've been, no, okay, I know, it will not crash, sorry. Yes. Okay, so, yeah, because I actually made sure it was okay, but yeah. So the idea is now we need to use tessellation. So tessellation don't understand standard primitives. Like tessellation doesn't understand point list, doesn't understand line, it doesn't understand anything really. So it only understands control points. So you have to say, I give you control points and deal with it after. So well, a natural choice is for a triangle, you can give 3 control points. For a quad, you will give 4 if you want to do a homography style. or if you want to do Bezier surface, you will need, well, for example, if you want to do a 3x3 Bezier surface, you will need 9 control points. But it only understands control points. It doesn't understand standard geometry, and generally drivers tend to hate if you provide them any form of those topology. Like ATI, it's guaranteed crash. So you can only choose between this list of control points here. And in our case, we're building a segment from nowhere. So we don't really need, we only need one control point, basically. We just need one point. But in that case, what you can do, because the problem is when you use tessellation, it's quite easy to select this by mistake, and then poof, bye-bye. So what you can do to secure the shaders in here, you can have this string topology, and you can set the one you want in the shader. So that means actually anything on this topology pin is completely ignored. You can just really say, okay, I can't work with anything else than that, so just give it like that. So now we have our point list, and we want to draw only one for now. So we have, the difference is we don't use a vertex count anymore for the resolution, because we're going to do the tessellation in the hull and domain. So our vertex count is 1 and our instance count is 1. So to build our segment, we basically say we just want 1 point, but control point, because it's just like this. So that's like little setup that changes is obviously you have the extreme pipeline setup of tessellation, which is just, well, you just get one and copy paste, because you don't write that by hand all the time. So it should be on every person. If you want to work with tessellation, you make a copy paste box of every type, because yeah, you don't want to write the setup by hand. It's just completely terrible. So we're gonna do it's pretty much the same as this vertex. It's still a simple line equation, but in that case, we don't know it's a line yet. So we just send the point. On the vertex shader, so what I give out of it, I need this vertex ID, but I don't really use it anymore, I said. Now we have the but I want to send the position, because I don't want to repeat the read of the position all the time. So it's a good job for the vertex shader. So the vertex shader will get, because now one vertex is one segment. Before, one vertex was one part of the path. Now you have to think one vertex is really one full segment, which doesn't exist yet. So it's really, one element becomes one segment. So yeah, we reduce the vertex shader work every time. So it's all, yeah, vertex process one instance. It doesn't have to process everything anymore. But getting the position is quite good, because it's common to every part of the segment. So we get the position in vertex shader, and we give it for domain to the tessellation stage.
Sorry, Vox, could you explain exactly why we need to use tessellation here as opposed to before?
Because in the previous one, the problem is when you batch, like when you start to instance your segment, you can't spread the resolution of the segment. Right. So that means if I want something like I want some places with triangle, some places with rectangle, some with hexagon, and same with really high res, super nice circle, I can't do that anymore. So the first example without batching was allowing it, and it was great. The second one doesn't allow it, so it's not great. So now domain allow us to improve that. So we have the same segment data as usual. We have the same for making in clip space. It's no big difference. The only difference is we have this hull constant, which will exactly hold our tessellation factor. So that's the new host for our resolution. We will have to write the resolution here at some point. So the first thing, what happens when we finish the vertex shader, so now we have set hull shader, which sets the hull will be well, you can do really crazy thing with hull, but like you can, if you have one control point input, you can output 60, you can reduce, you can expand. But in that case, we'll keep it simple. You have one control point as input and you output one. So once this one will calculate, get info of the patch. So on the hull, you can modify what they call patch list. The patch list, you can still modify it per patch. So now you're switching in a per patch mode, which in the case of line is still you per segment. But you will have to set at some point, knowing the whole control point data, you have access to the whole patch, of course. You can set the tessellation factor, which in our case, it's the user who provides it, so it's not completely difficult. And the domain shader is what effectively processes the tessellation. So the first thing is we finish the vertex shader. So the hull shader will assemble what it calls input patch, which is exactly the group of control points. Like if you said you have a topology of 9 control points, the patch will have to be 9, and you really have info about the whole thing. So in that case, we have only one, and you can say how much you want to output. So you can transform this, but I never had the use case for it, so I can't give you an example where it would be useful. So generally, if I have one as input, I have one as output. So domain is important in that case. We want to create line. We will keep the same geometry shader for extrusion because that part works good. But so now we have to say we want you to start your tessellation and we want you to build line basically. And partitioning is integer, so that means we will not take care if you have, for example, if you have a resolution of 6.5, you will just round it to 6, and if it's 6.7, you go to 7. So I forgot what's the exact equation for that actually, I think. But what you want is to, well, in that case, we just want fixed integer resolution. We don't want to do the in-between part. So because there's no in-between part, we keep it as integer. And output topology, we said we want line. So that's pretty straightforward. And that's this important part, which is the constant function. So basically, this is just processing the input patch, but we still need to assign this tessellation factor. And this is processed in the constant function. So in that case, if in the whole constant, you also have that, you have access to the whole patch as well. So you can, for example, well, there's other cases. For example, you could say, I really want a nice circle. So depending on the size of the radius, you could make it dependent on radius. So you have this more adaptive type of tessellation, this type of thing. So the bigger the circle, the higher resolution you need. So you have this type of case. But in that case, we want to have it user managed, so it's just our resolution parameter. So now we finished to have this line building, and now you have the domain shader, which processes is a line. And you have, so now it's called output patch, but it's the same data that you outputted from here. So it's the full, you still have access to the full patch because obviously that's when you need to tessellate. So that's when the data is the most important. You need to know what, in that case, it's not even that important, but for anything else, it is. And you have this UV domain location, which basically the tessellator, what it will do, it will take, if you set a resolution of 8, it will give you 8 points between 0 and 1. If you set of 64, it's 8 points. It's like a linear spread, I spread divided. So it's just a UV linear spread in general term. But the big difference is now it's set on the shader, so it is completely dynamic. So now we say we just want to get, we don't get vertex IDs just to get after when we will do batching. That's why it's already there. But now you have this uv.x. So from this uv which you had in vertex shader, now it's exactly the same, but domain is even nicer because it already returns it between 0 and 1. So you don't even have to divide by any resolution or anything. It's already done for you. That's very kind. And now you build your X and your Y, and so which is position and outer radius, and we send this to the geometry shader basically. So we build our circle in the domain shader. So we have to follow a bit of different step, but the technique is kind of the same. You get a number between 0 and 1 and you draw a circle. That's pretty much extremely simple. And so once you're done with that, the geometry shader provides you those line segments of the path that you do exactly the same extrusion. So now we have a non-batchable on tessellation. And what we want to do is obviously make it in one call. So now we want to say, I want to draw my 2000 segment in one go with the tessellation, but now because our tessellation is dynamic, we can set the resolution directly in the buffer. So that means we can do all we need directly from nothing. So now we have the null geometry. So now you can even choose if you want, because you freed one. So now I just kept instance ID, but you could use vertex ID as a identifier. I don't think there's a big difference for it. So you say I want 13 segment for here. So let's put 2000. But what to make it look so and we can see the you can see the resolution pin is not part of a buffer, but is quite available directly. So we still have our translate, so to move object, and now the only little problem is actually in our segment data. Well, we want a little more still, like because otherwise, well, for the moment we're only drawing white segments, which we want. So now we want to be able to have the resolution in buffer and the color in buffer. So what we can do is we can do one dynamic buffer on top for resolution and another dynamic buffer for color, but instead we're just gonna pack everything in one. So we have this segment data, so that's just like a description of what we need.
Can I ask you one question before you do it?
Yeah.
Line 88, so you have this output inner radius equals inner radius in tessellation ds extrude of x. There's
It's the one on the left.
On the left shader.
Top left, the shader.
Sorry?
That one, yeah.
Yeah.
Line 88.
88. No, like inside the shader in line 88, there's this like, yeah, the inner radius. So where does this, like the second inner radius, uppercase, where does this, like where is it defined?
So outer radius is done first on the circle, because I just built my circular path, so I just multiply.
But yeah, that's true actually. Good point. Sorry.
But where is the variable coming from? It's uppercase outer radius. So
Sorry, it's coming from here. So anything you put out inside the C buffer, it's if you don't have semantic, like here, it's when it does that, it reflects and just creates a pin automatically.
Okay. So sorry, I missed that one. But thanks.
Yes, that's how you create a pin that you can make.
So now, the only little difference is now we have our big batch. So what we do is we still have we still keep the transform separate. So in vertex shader, we do the same thing. We pass vertex ID, instance ID. We get the position of our segment. So exactly same process. But the important part is we need instance ID. So we need to pass instance ID to the rest of the pipeline because our segment data is in this dynamic buffer. So at some point we will need to read from there. So we need to know which is the segment number. So we go through hull does exactly the same because it just returns itself. Only difference is now the constant function has to get the segment data from the structured buffer to get the resolution. So now instead of saying we want this tessellation factor which is fixed or from an input, we need to get it from the buffer. That's about it. So it's no big, there's no really big difference, but in the whole workflow after, there is. And after, well, we arrive in the domain shader, so we need to get our segment data again. And we get, so from the segment ID, we get the data, and instead we change the full circle by the circle inside the buffer. So we just have to change phase, cycle, outer radius, and inner radius here. So the only difference is instead of having it from the constant buffer which creates input, we have this one, again, like same as when instancing any standard shader. We put something in the buffer, we put all the data we need in the buffer, and we are pretty much done. But the only little problem is we can't fit all that in a float for. So there's a bunch of little small example of dynamic plug which use DX. So the little difference is we're gonna do the little buffer in C# so to show it's really straightforward. So who doesn't do C# at all? So everyone does C#.
My man with the orange.
Okay. So okay, I'll try to go not too fast, but I guess it will be okay, explainable, I hope. So idea is we have a dynamic template, so it's the same. What we want to do is we want to just create a buffer which is big with this, and we want nice pins as well, because vector 4 was not so nice still. You still have to put some IO box to describe, whereas with pin we can directly set the value. So as soon as I create that buffer, I already have the right input. Okay, it's outer radius, whereas with float 4, what is W? What is X? What is Z? So with the dynamic buffer template, you can create just copy paste and create your own. If you need to fit data together, that's just a really simple way to do. So the idea is you have to build the struct you want, which needs to match like XLSL friend. So you have the struct in XLSL here, you have the struct in C#. There's no big difference. The thing is, XLSL doesn't understand color, so it just knows it's float 4. So the only difference is here we will set color because we want to, if we want a color in 4v, we want a color pin. If we put a vector 4, that will also work, but 4v will take it as data we want. So using color is just doing this, it's just, which is much more convenient for editing.
When you're developing your DirectX11 plugin, do you typically start with just a raw dynamic buffer, and then when you develop your struct and kind of finalize it, you turn it into what you're doing?
No, I do dynamic buffer up front. It's just for the sake of the workshop. I did it the lazy way first and then show the way I do it normally. I normally create the buffer up front because I don't want to work with X, Y, Z. If I'm really lazy or in a mega deadline hurry, and I have 2 people on my back, yes, or 2 plus, like being like with a whip, yes, sometimes I do it with X, Y, Z, okay.
But sorry, to extend on this, this may sound obvious to you, but what's the real point of doing this rather than even you could use a transform buffer and just hack it and push through on yourself?
Well, it's just because when you come to the code 5 months later, it suddenly makes much more sense.
All right, fair enough.
And yeah, it's quite really ugly on the code. Like if you start to use the individual values of transform, if you have a bit too much, you will have some unused part.
Yeah, for sure.
And you still need to pack the thing in a matrix in the patch as well. So it quite adds noise not only in the shader but also in the patch.
Yeah.
So that's.
It's obviously not as elegant as this. There's no doubt about it. Yes.
Yeah, and the idea is with the template here, you can more or less clone it and change few values. Like if you need to add anything, you add the struct input and you need to call sync and apply buffer. So idea, I'll just explain quickly. So you have this using here. Anyway, it's in the template. So if you clone, you'll start with the same. So generally, you can just I tend to not write it. I just try to clone this one and change the struct instead of recreating a new one all the time. But idea is you have here, you just have to use namespace to import the buffer template. You set up which struct you want, basically. You change your name and version, same as any dynamic plugin. And you set all your input properties you want. And the only difference is for buffer, I always use this pattern. All the buffer nodes use this pattern. You have this auto-validate. So that means if you don't apply, it does this sample hold behavior. So if you don't have the apply bung enabled, the pin will not go up, it will block. So this one will do exactly this. So that means if you actually put debug mode, and that's the worst example. If I put anything like plus value, that will do. And phase, but phase is UI node, yeah, here. So if I just now disable it, yeah, we can actually, that's quite interesting. So if we connect, but phase is below. Okay, that makes sense. Yeah, so if we don't use it, if apply is false, you can see that's blocking the input. So generally, a lot of buffers, like I have the case of extreme dynamic in that case, or I often have the case of this is something I just want to set once. It's just some static data that needs to be there only once. So for those, this pattern is perfect because once you finish to set it once, it's not evaluating anymore. So what you have to say is you have to call sync here because all the apply part is handled before you. And it gives you how many elements, and it gives you an array of them. So you have to sync and you have to fill the array with the data, and you have your dynamic buffer. So that's more or less it. So you just assign the properties, and all the fact of uploading to the card, dealing to multi-context and destruction, everything is handled by the template instead. So you just have to set the array of data and it deals with everything else. So yeah, if you can do either plenty of small buffer or generally, yeah, if I really don't have time, I tend to do that more actually. I tend to use more buffer instead of a struct. So I have one float buffer, one float 3 buffer, one float 4 buffer for every attribute, but then it becomes harder to maintain because you need to always make sure indices match everywhere, whereas grabbing one struct makes more sense. One case where splitting buffer is useful is, for example, yeah, matrix is split because matrix is per segment. So it's sometimes if you have data which has different use case, you might want them in separate place.
And what about in terms of optimization? Does it make much difference? Or?
It can be big, yes. It really depends on the use case, but tessellation can be really expensive. So small optimization like this, mini save of changing buffer location, so you avoid to read too much data or this type of thing can be pretty big. Yeah. Like if you start to work with pretty high res triangle and you start to have high tessel factor, you can push quite a lot of vertices on geometry. So any small thing becomes big. So, but it's not something you can know upfront. So you need to try out a different version, and for your use case, this one will be faster. So you need to timestamp and check your frame rate and use timestamp to profile. And from that, you will find, hopefully. But difference can be 6 times or 10 times faster sometimes. That differences can be really insane.
One question about dynamic plugins. What to do to not use the references from version 3?
That's in that node actually. You have the trick in that node. So the idea is you have to it's really, trashed it again or what? Maybe I did not do it on this one. So on next section I'll explain actually, because it's on other projects. This one's not been done. So you need to replace this thing by something else that I'll show you.
Is it the
yeah, you have, actually you have it around, do I have it on this one?
is it
card thing when you do?
Yeah, it's a
that,
bit something like that, yes. But it's not on this one at all, so I'll show it on the other example.
Yeah, thanks for highlighting it. Super headache that.
Always.
Yeah,
So so yeah, now, well, the only limitation, because there's always, I mean, with every technique, there's one thing which is mega cool and one thing which is mega annoying. That's why I presented them all, actually, because then suddenly you can choose the one which fits your case best. But none of them is perfect. And the big problem with tessellation is your maximum resolution is 64. So sometimes if you want to really have a huge circle in the middle of the screen, 64 might not be enough anymore. You have some trick, but then to start to mix more than 64 with a really low, like 3 or 4, it becomes really difficult. It's quite easy to reach more than 64. You can do 2 vertex. You will do 2 vertex per segment instead. So one vertex will be the first half of the pass, and second will be the second half of the pass, which is, done that quite several times. But the problem is every time you add, so if you want 2, 5, 6, you need to multiply by 4. So that means everything will be a minimum of 4 as well. So that means if you want to really mix low res and high res, you probably will want to have 2 shaders anyway. So you'll have one doing the very heavy tessellation and the one which does the low key less than 64. So you can also, you don't need to do everything in one go all the time as well. Sometimes you can do things in 2 or 3 calls. It's not, I mean, you can do 30,000 calls on good card nowadays. So you can totally, like saying less call, yes, but you can still, sometimes using more call is better. Actually with tessellation it could also. Because very high tessellation is very expensive, so you might also have one version with low part and one version with a high part. But in that case, yes, you're limited to 64, which is sometimes an annoyance. So you have to choose at some point what suits best.
So the tessellation the final step, or can you like tessellate after a tessellation step?
You can with using stream out. Anything which comes out of tessellation, you can push it to stream out. Yeah, so you can either push the lines and extrude later in another pass, or you can push the fully extruded segment and then do something else. So you can tessellate it again, but then it's different also, I forgot, because now it's triangle, it's not line anymore. So now you already transform your geometry into something. So it's a bit more complicated. So you will need to tessellate triangle and make sure to thin the edge. So you just need to normalize the edge because it's a circle. So to make sure you continue, because when you interpolate triangle, you interpolate along a line. So if you start to tessellate again in a second pass, you'd have your, I'll use my favorite tool again. Well, I have my arc here actually, but so now if your resolution is here, like if you have your part of segments this way, your interpolation will be done on this line here. So that you don't interpolate in a circular way.
Better performance by doing the instancing in Paint?
Sorry? Instancing in Paint? Yeah, I don't know. I have to do a 4 kilobyte picture, so what does that make inside? Saying that's something like that. So, well, but for interpolating a circle to put it back, it's really straightforward because you have 2D vector and you normalize it. So you make it back to length of 1. That's the simplest trick in the book. Or you can recalculate sine and cosine if you prefer, but generally just renormalizing does the job quite fine. But in that case, yeah, you will need to take edges of triangle, so it's quite raw. You can, in 2 pass, you can extrude first segment like as ISO line, and you can re-extrude the ISO line to another ISO line in a second pass. Then that one will be quite more, probably easier. And then you extrude in the last pass, of course. So yeah, well, with this one you can do some quite nice infographics, because all these mini statsy type of graphics use a lot of these things. So being able to have a lot is, well, good. So that's for the line tessellation. Well, line tessellation, there's not much documentation. It's a bit underrated to my taste. You can really do nice things around with it. Like you can also, you can really do whatever you want after. Like if I take my, so factor, which is here, I just put 64 then. And if you put more than 64, by the way, it will just skip to 64, so it will be clumped. If you put less than 0 or 0, it will not draw anything. So if you put a tessellation factor of 0 for anything, you just discard the patch, basically. And I need to be... Yes, so now if we have our circle, you can totally start to do different things. So I'll just do it as a quick example. So now we have inner radius, but we can still, store, did I store the UV or not? No, so I'll do another version. So at least it can be copy pasted. Yeah, so now idea is we're just gonna use a small formula to change the thickness inside the same patch. So segment dynamic and thick pattern and thick. And actually what we'll do is, instead of trying to use a crappy formula, we're gonna use a texture. So now we have our 3 circle. Actually I'll just use it for 1, that will be fine. It's exactly, well, it's not going to be spreadable because it's in a texture, but so we're here and we need to set up our resolution to a lot. So we have this very big one, but now what we want is we want variable thickness. So what we'll use, I often use that one, like B-spline here, and I just copy paste because setting up IO box is complete nightmare. So I just take that like this, and we'll use this as a curve. So this will be the thickness along the segment. So it's a bit more designer friendly to do it that way, because if you ask a designer to go in shader code and change sine and cosine, he's not going to be too happy. Whereas using well, control texture is a bit more designer friendly, so we'll do the designer friendly version. So now we have extrude, and we'll say add one more texture style. Yeah. Okay, and so first thing we need, we said, so we have this curve here. So instead of using a texture, because we're just thinking in 1 dimension, we use a texture 1D. We don't need to use a texture 2D. So it's important to use texture 1D. You could use a buffer for each control point to filter, but because we don't know the resolution necessarily in advance, well, with a texture 1D, you can use a sampler. So if you search in between, you can interpolate. So you will make sure you always never have a mini cut of resolution, because the sampler will always make sure you interpolate exactly in the right position. So if you send a texture with a resolution of 9, it will still interpolate nice of 128, sorry. If you send high resolution texture, it will still find the right place. With a buffer, it will be much more complicated because you need to find between which and which. So we'll just use our nice 1D texture. So texture 1D inner radius texture. And we need a sampler, so same thing, that's going into constant. Yeah, we want a linear sampler in that case because we really want to interpolate. So yeah, that's a simple sampler on our inner texture. So now the only little difference is we were missing, we don't have the UV anymore of the segment. So if I consider UV in that case, it's I have to consider cylindrical version. So basically, it's not UV like 0 to 1, that's a planar UV, so if I want to map a texture onto it. But what we want is, we want the cylindrical UV. We want to know where we are depending on the radius. We want to know where we are in polar coordinates. We don't care about the UV of the box. We want to start to read the texture in that direction. So actually in that case it's easiest because that's exactly the UV of the circle equation, which we already have. So if we have our GS input here, which is here, we already have inner radius. So actually we will just have to change it, that's it. So what we'll do is we'll just completely use texture instead for now. So it will be texture.sample level because we only allowed sample in pixel. Linear sampler. And so, well, U is our uv.x, so we don't even have to calculate anything. It's provided for us. That's perfect. And we need level 0.
Quick question about sample level with 0 and stuff.
Yes.
I've done stuff where the 0 is actually dynamic number. I was just curious to see what happens when it's a float.
It interpolates in between the MIP levels.
Wow.
So that means you oversample a bit, but yes, if you put 0.5, it should interpolate in between.
Very good. Nice.
I can double check that after, but it should normally, as far as I know, it does.
Yeah, because it looks really smooth, and I was surprised that
it will, because it's like when you use the float tessellation, it still builds triangle, but it collapses them to make sure you have smooth transition, and sampler will be the same because obviously otherwise you need to have a progression in the sampling. If you had cuts every new level, it would be horrible.
Yeah, that's right.
Yes. So now we have actually just replaced our inner radius, which is constant. We just replaced it by the texture version. So texture version is just a float, so we do a dynamic texture, 1D. We need only one value, so the bigger resolution on resolution of the sphere here, since it's 64, it makes no sense to put more than 64 because, and channel count is 1 in that case because we just want a radius, so it's one float, so one channel. And the 64 will go also to the linear spread here. I always get this wrong with the spline though. Okay, so we have our dynamic texture and now we feed the data to it. Well, so yeah, now we can use our texture to really quite model a bit more nicely our element. What's kind of, well, obviously adjusting curve is, well, it's a bit easier to fine tune this for this type of thing. It makes no calculations are really complicated. You want to just fine tune your value. So you can use any like spread editor or function like those. And yeah, one thing is here you can also suddenly change. So for example, out here you have inner, but you always have this fixed circle, but you can also expand in both sides. So float x equal. And instead of here using a fixed inner, and let's multiply by, let's do it equals x. And instead here we have this outer radius, but we can also multiply, it should be plus x. Oh no. So you can also do it in different directions. So you can start to model differently. You can start to, if you start to modify inner, you can also apply the same technique to outer. And if you have like, there's none of that one. So that's one of my to-do lists to do texture 1D array. Because with texture 1D array, you could also send the different slice of thing. And when you instance, you could select which pattern you want. So you can still go, well, you can really go deep and deep and deep into that type of graphics. But everything with the more you offset, the more options you have, but the more you have to think a lot differently about how you prepare your data. Like before you were here, now you need to use a texture for this, you need to use a buffer here. So that's it for the line segment. So now I'll just quickly show quad. Triangles, there's quite decent amount of example in the, I'll see if I have time, I'll pick one up and I'll explain it also. But triangle is a bit, there's more examples which are already there. But quad is a bit less known also. So we'll do a quick quad. So we'll just do a quick quad animation. So we just have bunch of, like now we're gonna do a bit of grid. So the idea is we want to have a quad and we want to transform it to a grid. So we want various resolution. But instead of building it in GS, we're gonna use tessellation to build the grid. And we want to apply different size to the subpart of the grid, basically. So that's the idea of here. I don't know if there is text code here, actually. So, well, first thing is, yeah, in that case, we have our square, and the idea is to subdivide it again. But this time we'll, because instead of doing it in GS where we build those grid indices and everything, now we will basically build it in tessellation. So the easiest way to start with a grid in tessellation is to use a quad, which is a grid with the minimum possible resolution. So basically we start by this, and if I put factor lower, factor is not dynamic. Well, yeah, we start with simple quad basically, so I don't think it really needs any explanation, but yeah, we start with this graphical part, in which case actually, because we will divide inside, we don't really need even the triangle information in theory. We only need to say, we need to think actually, like tessellation is control point, so we can think of the quad as control points, and you have 4 control points, and you want to build a bunch of quads in there. That's exactly what you want to do in that type of scenario. You just want to build quads inside the quads. But to do it in here, so what we need to do is we need to say we don't need the triangle information. So anyway, topology will be in that case 4 control points, because every corner of the quad becomes the control point. So like we need this information to divide elements in between. Then when we have those, and we also need to say we just want those 4 points. So we need to, for the moment, our quad as index buffer. So it's thinking of 6 elements. But what we need to do is we need to say, oh, you can just treat the 4 corner as control point, don't care about the rest. So for that, we need this per vertex drawer, which will say ignore the lookup table of indices, just draw the vertices on their own, because that's the control points we need. We don't need any assembled version. So now we enter the tessellate quad. So it has a few includes for, well, famous most overused IQ noise function. I think that I've seen that in every part of the world. Yeah, if he had €1 per time someone used that function, I think he would be a proper rich guy. So you have just a bunch of wave functions. So it's like you have a 3D position and you get a float value. So you have a sign on the x-axis, a square sign, which will mean instead of having a smooth curve, you'll have a square, well, a square wave that you have in audio processing, basically. So you have sine wave or square wave. So square wave is just, if you over than 0, your maximum. If you under, it's just a sign of the value, more or less. But don't use sine for that because it's quite slow. So it's better to use just, you can just use greater than 0 and it does the same. Because in that case, we also don't want the negative value. So it's like a, start to like that. So yeah, if we have our origin here, like our square this time is like this. It's like this with a broken 1/2 wave each time. Because we don't want to go negative side, because negative side will flip the triangle. What we want is every time you lower than 0, you just don't display the quad, basically. So, well, that's just some sine function which all have a frequency and offset because we want to animate them. No big, like anyone which works with synthesizer will feel at ease, I guess. And there's a bunch of extruder, we'll see them a bit later. So let's start with the arrival in the shader. So since in that case we have control points, we don't really have to do anything in vertex, we just receive the 4 points of the quad. We could transform it also in that case, it's just not done, but the quad could be transformed here, but since it needs to be sent to camera, it makes no sense to transform here because we will need to transform by view projection at the end. So we can just leave it for the end. So vertex is quite a proper minimum. It's just, you just return yourself. So every corner returns itself. Then you arrive at, as usual, we arrive, where is it? In the hull shader, which says now we have a quad domain. So triangle will divide triangle inside triangle. Quad domain will actually divide as a grid. It's like a grid divider. So like same thing as this grid we did in geometry before. It does exactly the same concept. It will build you a UV in one axis and it will build you another UV in one axis. And it will build you rectangles. That's exactly, so it's a grid generator which is automatically done for you. So what you done before, like the pipeline can also handle it in tessellation. So this one does exactly the same, so it does nothing as well, it just returns itself, there's no more work needed. And here we use a fixed tessellation factor, which is here. Not T factor. Ah, okay, why is it named differently? Ah, here, that's this one. So here we have a 16, but if we put 4 or 32 or 64. We can't go more than 64 by 64 per quad, obviously. A tessellation limitation of 64 is all the time, so it's not for any type of primitive, it's for everything. So you will be at a, but so yeah, from one quad, just on the card, by using tessellation, you can build some quite high-res elements. So let's do it for now, and you can obviously change it. You don't have to rebuild the grid. It's not even caching it, because here it's just a fire and forget. Every frame, it takes the quad, it builds the grid out of it, and this grid is sent to the rasterizer, and it just got rid of. That's it. So it's not memory free. So be quite, like when you use tessellation or any feature, it will need to use internal memory. So it's not free up to, like thinking, it's not in a buffer, so it will cost less memory is not completely true. So it has to be a bit careful on that. So, well, let's use a lower factor for now. So now what we have is we have the tessellation factor, so we can change, maybe I'll stop animation for a sec. Where is it? Here. Here. And let's move that. Okay, yeah, so here we can see the exact tessellation, but you have different for the edges and you have some for the two inside. So for example, if I put 4 here, you can see like the inside, it will mean make me a grid of 4 on the X. You want 4 columns for inside 0. And for example, you can say I want 8 rows. And here you get 8 rows. And for the edges, you have a bit more. So now you're still on 16. So it will also divide that for you. So it will also evenly divide. It's already done for you by the pipeline. You have to do nothing. That's quite awesome, because this calculation is quite a pain. So instead, the pipeline automatically calculates the right tessellation for you. So here, the inside edges is very useful if you start to have separate elements next to each other, because you will want to eventually have a resolution of 2 here. But if you have elements which are next to each other, if you start to have very different factor, you will have cracks in geometry. So one side will have 16 and the other patch will have maybe 2. So that means if you have a displacement map, you'll have different resolutions. So you will have mini cracks in geometry. So edges are really designed for that thing. You should actually calculate what you want from neighbors as well. And from neighbors, you use whatever. Yes?
Maybe it's the same question we get it, but if you enable animation,
yeah.
If you now enable animation,
Yes.
and then you have like this shrinking pattern, then you get like this weird behavior on the top and bottom both that it's, at least on my idea, that.
Yes.
So is this the same?
Yeah, because here at the end you still get triangle actually. So that's a bit of the issue with those. Like the pipeline doesn't know about quad. Like quad does not exist. So you receive triangle. So you will need to apply another function to be able to apply the animation. You will need to make sure to get the center of the quad to make sure to reduce. So yes, that one is not perfectly correct indeed.
Can you explain? So before you change the shader to the 4, like when you're using the T factor,
yeah.
Like this didn't apply, but I don't understand why. So maybe.
Because here I also wrote some by hand.
Okay.
I just wanted to show that you have tessellation factor are also different. Like, for example, you can, if I disable anim again, like here, and if I disable animation again, and I put like 64 on this one, you can see, yeah, like every edge can have its own factor because it needs to match the neighbor generally to avoid the cracks. So that means you need one factor for each of them. And then the inside can be interpolated. So for the inside, you can put what you want, but you still often need to put a different one for each edge, depending on your use case. In that case, it's actually not used, but generally anything when they do landscape rendering. For landscape rendering, that's basically the technique. You have elevation map of each, and you need to use a maximum factor to preserve the resolution. So, but let's go back to here. So that's our grid subdivision, so nothing to here. And then we arrive in domain shader, which has this UV, domain location. So this UV is exactly a grid UV. So it's like you had, instead of every time we spend time calculating, that UV grid have been done for you. You give the parameter to the tessellator. Basically doing this in vertex of thing, you do the job of tessellator. So it has advantage also, the more than 64 res. But so in that case, you have the grid UV, so well, and this one is also designed, so it's actually doing Bezier interpolation. So for example, that if you have a grid like this, what it does a 1D Bezier in 2D. I don't know how to name that. Well, it does a 1D Bezier patch, basically. So it's a bit like, homography or this type of thing you have in mini mapping tools. You always, you have this type of things everywhere. But so that means it doesn't work only with quad, it also should work with corners. So if you do vertex geometry, buffer. Which one is it already? I don't use that one that often. Okay, let's be lazy then. So if we use, we'll just use a dynamic. We're gonna just replace. So the quad has a 4 corner, but I'm lazy to refine which one to do. So we'll just actually grab. I'll do it as another one, so it can be also. Well, it will be all the final part is gonna be back in the country, but I'll put underscore final. So you can just grab the before and after version. So Sam, don't worry about trying to redo it yourself. It's no point. So here, and instead of building our quad, we're just gonna do a null version. So we're gonna send a null geometry, and we're just gonna put the 4 corners in a dynamic buffer, like so. Dynamic buffer 3D in that case, I guess, will be the best. And so here we say we want a null geometry, and we want patch list with 4 control points, and we want 4 vertices. So we don't provide the 4 vertices in the vertex buffer, we'll just send the corner in a dynamic buffer. It's generally more convenient, like because this we can then edit them, so it's just more convenient. So we send that, we already have topology, so we should need nothing. Now, obviously, it will say layout is not valid, but we don't care too much. We're gonna change it. So, I need to also clone it, quad underscore null. So difference will be reasonably straightforward. The first thing is VS input. We actually don't use the UV, so we can completely get rid of it. There's another one with it, and after DS will be okay. And yeah, UV. Okay, so we in that case UV equals UV. Okay, so now it's still drawing nothing because now we did not provide the geometry in the right format, because now we are sending null geometry. So we need to provide this control point data in different way. So the VS input here, we get rid of it because we don't have vertex buffer anymore. So we just have uint iv sv vertex id. And so now we have a dynamic, structured buffer float 3 SB corner, and now we say return SB corner IV. Ah, yes, okay. Okay, in that case I will just get, you can also, if you have only one variable, often just doing also this one, so you can just put an out parameter like this, and like so. So it's completely equivalent to create vertex output and output it, but sometimes like, well, same thing like deadline or just one variable. When there's one variable, I tend to do it that way. But it's complete preference. Like some people like to have it in struct, some don't. It's just complete plain preference. So I'm not giving advice on what's better or not. It's just completely up to you. Ah, yeah, but I still need the struct because it's yeah, because you can't do that though in the, you can't do that in GS and hull. You can do it in pixel shader. You can also put the target as a out. You can do it in, well, compute you don't because you never have in-out. Compute is always void. So, but in vertex and pixel, you can use this out version instead. And now we need the 4 corner. So they are on our dynamic buffer. And here, 3, 4. Ah, a call row page. How is it? No. Page. Okay. So if I remember right, the order, because we need to provide it in the same corner, needs to be in the same order. So well, I guess by trial and error. So okay, that's all -1, -1. I would expect it to be like this. I would expect I did counterclockwise. Let's see if I did that. No. So that's this one first and this one next. Okay, so now we have our grid back, which is cool, but that also means if I go back to offset, let's try to find. Can't I have one? Ah, square. Perfect. And frequency. Ah, here. Okay, I just change for now. So now we have our grid again. Perfect. But the thing is, yeah, we can also move corner. So all these mini corner mapping tools, if you're quite lazy to build geometry, you can just do it in tessellation also. So every time you move corner, you will need to rebuild your whole patch, whereas here you can just directly move it and tessellate it all the time. So you can put it in a stream out as well, and when you're done editing, you disable the stream out renderer and you're done, basically. So it works quite good that way too. So yeah, actually it's exactly the same as, actually not this one, even the 3D version. Ooh. Okay. Yeah, it's exactly the same as this version, but only with, yeah, you have control point resolution like this. So it's the same version, but instead of building the geometry all the time, so every time you change control point, this one recalculates, but this one is a bit more slower because it's a bit more flexible as it has all dynamic resolution. But instead of this, you can also tessellate directly in domain. You can do 2D, you can do 3x3 version in domain. You need 9 control point on to apply the Bezier. So you can do any version you want, but in that case you will need a different shader for each. So you will, it's really, really difficult to mix various control point resolution in the same shader. but in 99% of the case, I only need this one and the 3x3. In rare case, 4x4, but yeah, 3x3 and 2x2 are by far more common. And camera needs a reset probably. So now, we have our quads. Only little difference here, you output your vertex and the quad tessellator has a domain of quad, which means quad domains means you output, it already does the quad expansion. So it has the vertices and it builds 2 triangles. So your geometry shader will receive 2 triangles. So now we reach the geometry shader and it's, which one is it, this one? Technique per square. Okay, so it's GS. So yeah, GS will grab your 3 triangle of your quad. It will build a distance of edges. So it's the maximum edge distance. And it builds, well, it has some wave, it builds a wave function basically, so you have this sine function. It's just for animating it, so if you have if you do your mini quad corner, you can also just put this and do some animations on top quickly. So all these are really quick to change also, that's why they work really good. And so yeah, if we animate again now, yeah, you can switch also which type of pattern you want. So that's a square on the y-axis. That's absolute value. So it builds it from the center. Radial is gonna be circle version. So if I put it in local simple, so and square radial will be the circle. I have to recheck. I think I don't remember what quad does. It's output topology where you decide.
So if you go back to wireframe mode.
Yes.
So is there like a reason why like in the quadrants the triangulation flips?
That's the tessellator who does that. Yes. And the reason for it, that's a good question. I would think it's coming because of the edges at some point, but I am not too sure. I am not sure. It's the tessellator which does it like that. I'm not sure if there's a valid reason for it, but I guess they thought about it quite a lot. So I guess there is a valid reason, I just don't know it. So yeah, after you can just use, well, any function that gives value, you can use it as amount. You can quite switch them reasonably easily. And yeah, you can choose trend, so you can say I really want it to go to zero size if it's not visible. So you can, yeah, you can really add tons of animation parameters and you can change them in real time. So the whole, when you have tessellation pipeline setups, the real advantage is you can have really this really fine-tuned control really quickly. You can go change, you can change quickly a mini formula and then you just create, you have your parameter out, you can tweak it, animate it. You can sample you can sample level as everything non-pixel. So yes, you can sample. You can sample every stage basically. The only thing is you can only sample level pixel. Pixel shader are the only one where you allow sample. All the ones you need to do sample level.
Yeah, I mean, it was just if we would use like the intensity of a texture.
Yeah, you can.
To, like, set the radius of like these spots.
Well, I guess
similar to this inner radius we did before with the
Yeah, I guess. Well, I'll do it with. Yeah, I'll do a noise version quite quick actually. So we'll just use our favorite Perlin friend here, and I should already have a slot for it. That's awesome. But that's not anymore. Let's get rid of this actually. Okay, just get rid of that one because I'm not using it. So PS for yeah, it's just sampling for now. So I'll just make it return 1. And we'll use our texture. We'll use our texture 2D here. Yeah, in that case, yeah, we can do it here. So which one will be the easier? Yeah, that's gonna be this one. So do we pass UV? Yes. Okay, level please. And it's input. Well, that should be. CW. But next. Well, I need to put the UV. Well, I need to either pass UV. Well, I'll do it like. I need to either repass UV or just obviously put them in the right. Well, normally you add a texture transform for that, basically. Any texture has a texture transform assigned with it in theory. But yeah, you can assign height map to control any parameter. So this one controls radius, but you can redo the mini ring version. So you can use one to control inner, outer. You can use texture, you can use buffer. It's but for those, well, texture is a natural candidate, let's call it that way. Because they're also quite easy to, height map are quite easy to compose outside as well. So yeah, you can like push them away. Well, you can really apply any geometric transformation, translation, rotation, anything. You can really apply any of them directly. So once you set the pipeline, you really have tons of freedom, which allows you to do this type of things, which are really difficult. If you were doing it by CPU or without tessellation, it would be quite really painful. That adds quite quick. 64 by 64 quad, well, that's, if you start to push like 100 of them, that starts to, like that's your resolution. So if you start to push 100 quads on there at max, you already at 250,000 primitive, 500,000, sorry.
I was more like thinking about like how does the tessellation shader compare to, let's say, the geometry shader. So like past like 4,000.
Yeah, I think it really depends on the card also. That's not something I would give. Like tessellation is not, well, the fact of entering tessellation has a cost. So just the fact of using tessellation, it's the same as using geometry shader. As soon, even if you do a pass-through geometry shader, you will have a cost. And tessellation is the same. It has a cost of using tessellation just for the fact of using it. Actually, even enabling it and disabling it. So that means normally people can try to group their shader, like everything without tessellation and everything with tessellation, because just triggering it on has a cost on the overall frame. So you want to switch it as less as possible. But that's micro optimization I never needed ever in my use case. So I guess, well, maybe one day, if one day I need that, it means I'll have optimized every other part and it will not happen. But GS has quite a cost because it costs on the rasterizer. Instead of sending, it has to assemble the primitive. It can't do any early operation on it because when you, like you can direct, if the triangle is, well, you can do the face curl, which is, well, just a simple dot cross product operation. It's really fast. But then when you get geometry shader, all this has to wait. So you have to still assemble the primitive, provide it, get the result, and then try to reapply all the culling. So that it's not free, but it's still better than CPU version. And it's less cumbersome than compute version at the time. So it's a bit, it's good, it's the best middle ground.
But so compute shader will always be faster.
Well, the advantage, yes, it would be a lot faster because it has the advantage, but you don't have the tessellator. So that means you have to build all the tessellation by hand. So you have to build, and to build a dynamic tessellation factor in compute, it's decent amount of work to do it properly because you need to do the sums of, it's quite pain. Compute has a big advantage because what happens is the pipeline gives you an order guarantee. So that means when you process your vertex shader, if you send the same vertex buffer twice to the same shader, you will always have they will maybe process vertices in parallel, but it will make sure everything is in order at the end. So that means if a triangle is the number one in your buffer in one frame, on like basically it will always arrive in the pixel in the same order. So that means if you have this triangle number one and in your index buffer and then have triangle number two, the pipeline on the rasterizer all the way through will make sure to preserve order of processing. So if you do stream out twice, you will have exactly the same output data. If you do stream out twice on the same buffer, you have guarantees that you will have the same data. Even if you append with various things. If you use compute, you might have same data but in different order. And the order guarantee has a big cost, but has of course a big convenience too, because you have this order guarantee, which you have to take care yourself or do in case you don't care. So compute, it's not, yeah, compute allows you to not care, so because it doesn't have to wait for order. As soon as it finishes one batch, it can actually, even when it's partially finishing, it can even start new batch anytime. It doesn't have to wait. So it can say, this batch is finished, this one is still running, run this batch instead. Whereas geometry shader and vertex, they still have this waiting point. But yeah, compute has tons of other advantages that I think I couldn't, well, spend a day naming them. Yeah, the biggest drawback also of stream out is you can't, unless you have a non-automatic factor. If you have if you don't know how much geometry you push because of this condition, you only can use this draw auto, so you can't instance the resulting geometry. So you can't take the output of a stream out and say draw 5 instances of it. It's not possible. Whereas with compute, if you do your compute setup, you can do the same type of pipeline, and you can also say, oh no, this geometry draw instance version of it. But compute has a lot of, it's tons of more setup to do it beforehand. So the setup time is really longer. So that's why GS is the best tool for hybrid. So yeah, and you can see quite most of the time the whole things kind of always end up with doing null geometry. Like every time you have plenty of the nodes done in CPU, and they because of the convenience, they tend to just disappear of like, well, we don't even use an input anymore. We just use control points here. So here, and guess that's it for tessellation. So I'll show, well, that's almost there, I guess. Yeah, so there's a couple of other last example I'll explain. And yeah, so it's the idea, there's 2 or 3 things which are very useful for DirectX11. You can, I did a few dynamic plugin template. So they are very simple dynamics. There are no crazy big rendering and everything, but sometimes, like for example, it's very easy to do a custom layer plugin and to do sometimes to do a bit of strange routing and things like that. It's very convenient to, instead of, it can be really difficult to patch, so sometimes a small dynamic can also make big difference. It's very simple, but it can be really effective. So first thing is there's this, who knows exactly what validator are in the DX pipeline? It's not a Microsoft thing, it's me who did that. So, but it's who knows what it is or not? Who doesn't? Okay. So I'll start by that. So idea is basically, well, validator is was always from doing years of project with 4V and going through the same pen ever and ever again. At some point, the idea is something needs to be done for it. So that's, and the biggest problem was always sometime we want to draw something, sometime we don't. And it's to be able to have a bit this select at layer level. So that was the exact concept of solving it. So if you consider, for example, a constant here, and I'll just do another group for now, and we just do a bunch of boxes and random ones. And translate, of course. So I'll just put 60. And now we have a random spread of hue of color. Just well, it's no really anything interesting, but well, there's always been this eternal problem. Now you want to say, oh, I want to draw this box only if it's within a certain distance of a point, for example. So I want to say only if the distance of the box from the box to the origin is lower, if it's inside a sphere. That's exactly what the example does. So the idea the idea is always to do a distance. You do a distance 3D, and that's distance 0 with the origin, so in that case it's okay. But well, if you want to do it faster, you just do normalize 3D vector and get the input, get the length of the value, because you're using origin, but if you want to move the sphere, obviously you'll use distance, so it makes more sense. So that will be the center, and now if it's lower than some radius, like 0.2, then we need to start the big select chain. So you need to select color, and I should use the same amount, so 60 and 20. Perfect. So you need to select the color here, and you need to put it around here. And you need to select transform. I hope it's there. Yes. Okay, so and you need to select your transform here. And of course, we need to change radius. Here we go. And so, yeah, so we decided to draw only the box inside this sphere, but we can already see the pen because we have just transform and this HSL join, and we have to select all of them. So that means if suddenly we have diffuse specular reflectivity, so when we have suddenly like 10 pins, you need to repeat this select on 10 pin. Every time you add a new attribute, you need to find the right select. Remember to attach it to the right value. So instead, the idea was to say, when I'm rendering the object, I know the object location because it's a transform matrix, and we know the object we know the object data. We know the camera, like the camera is provided like from here upwards, all the camera, view projection, render size, it's known by the layer. The layer knows all of your render data because it needs to send the transform, the view transform needs to be sent to the view of the shader. So we have to, so the layer keeps the knowledge of the render settings.
Does it also know something about maybe the color or some pins you fed into the shaders?
Color, it does, no, layer does not, because layer is not yet, it's up to here, so it's not up here. So it doesn't know yet about geometry. So you have the layer only knows about what's done. It's like you really read the graph in reverse with layer. It's not different from DX9 way. You always read different from here to here. But now we know what type of geometry. We know the bounding box of geometry if it's provided also per slice of shader. The shader knows that. So the idea was to build something in the layer which will say, I give you the render settings from the renderer, I give you the object settings, which is the transform in geometry, and the index of the object, and you tell me yes or no, you can draw it or not. So for example, instead here, so you have this within sphere, which is the opposite version. And so anything which is outside of the sphere is removed. As anything which is inside in that case. So, but instead of having to do all this selection, instead you can provide, well, you have a few which are already provided. So you can say, I only want this slice. You can say, I want this range of value. I want to remove that slice from drawing because I want to draw it somewhere else. So for example, if you have one sphere that is selected, like, I don't know, let's do some, I'm sure actually validator, that will do exactly that, this one. Remove slice. Okay. Well, that one is just a countdown with remove slice, but what you can do, for example, is you do get slice validator, and you do a group, and another validator. And a constant here, another one, and slice is the same here. And we need to set the transform now. So now we don't see it anymore, but now let's say we want to do a small inner radius for segments. So you can suddenly say, oh, and I want to draw this one with Guru, for example. Well, it makes no sense in the case of segment, but but so the idea is validator will say anything but this slice should actually be drawn, and this one will say actually only this slice should be drawn. But you can do it at layer level, so you can all the select parts that you have to use, and if you have to split, you have to do this select part with not node and do it in other parts. You can do it with the validator at layer. So you have a few like of them, validator, layer, frustum. So this one is auto if you're outside of the camera. It needs to know the bounding box, this one. So you need to know the bounding box of object. but it will check if the object is outside of the camera, then don't draw it. So it saves on performance. If you have a lot of objects which are a bit scattered, you can say just put that, and it will normally tends to increase your frame rate from 0, so it's quite useful. It's like a really nice free. It's in the worst case it will cost you a little, but if your objects are not all on the scene, it tends to get you some quite good gain. You can see how many first test. You can see also how many elements passed and failed. So you can say, if no element fail the test, then maybe we should disable it. So you can also make this type of decision. Yeah, all the geometry nodes do that in advance. So every geometric primitive calculate bounding box, and all the 3D model loaded from Asimp actually. They all calculating the bounding box as well. So yeah, only thing is with StreamOut you have to write the bounding box thing yourself. There's quite some ways. There's plenty of different ways to do that. You have to do it either in compute, or you can do some form of pipeline strings. So yeah, there's plenty of different validator styles. So for example, this one will use different. If you have different viewport, it will make sure each slice is assigned to a single viewport. So well, but the thing is also if you because well, validator is just a C#, so you can actually just also, if you don't have the one you need and you need a custom selection, you can just also have the template cloned. Speaking about that, I'll speak to it right now. Yeah, you need to do that on the pass, basically. That was the question before. So you'll see it, well, you have it in the template, so you can check it again. But you need to put this value in the reference pass. So it's every time you clone a new one, you need to do it every time. So it's like 4v always overwrites it with some weird value. So you have to redo it on every new clone. But it doesn't take really long to just go copy paste this. It takes 2 minutes. But yeah, it can be, if it doesn't find the reference anyway, it will still use the last compiled version. So it's not too bad, but yeah. So now the idea is you can also write your own validator. So idea is you have, validator is just an interface. So the idea is you have an enabled, so well, Boolean to tell yes or no, I want to be active or not. There's no, and in that case, because it was not available, I did the bounding sphere one. So within sphere validator, so draw if you're inside or outside, depending on condition. So obviously it needs a bounding sphere to work. So that's a slim DX type. It just represents a sphere which is center plus radius. And now you have this validate function, which is object settings. So it's per object, it will contain the information about the object which will be drawn eventually. But if you return false, the object will not be drawn. So you say, yes, it's a barrier. You say yes or no. It's really like the last moment before the pipeline starts to do the drawing. It kicks in and says yes or no. So you implement these three methods, like set global settings in that case is not useful, but it will call it only once per shader. Like this is called, validate is called once per slice. Set settings is called once per render. So every time a layer calls, it will pass, say, hey, by the way, this is where the camera data is. So if we check settings, for example, you have aspect transform, which is from your renderer. That's crop transform from your renderer. You have quite a few ones. It tells you if you're in depth only mode, how many draw calls the shader expects to do, which geometry, but that one is a bit special. Layer order is the other ones for ordering. Validators is eventually you can have more than one validator, so you can say, I want to be inside, it works in an AND fashion then. So you need to, if you put it twice, it will be if you're inside that sphere and inside that sphere. And so yeah, you get that ones are a bit low level things that normally they should be a bit more hidden, but that's not convenient. Like projection on row projection. So row projection is a projection pin transform. So that's a projection from the pin. That's row projection. And projection is actually projection with the aspect and crop applied. And yeah, you have, well, render depth, height, so you know the size of the texture. If you're rendering to a texture, it will, render space is a bit of same version as camera, so it's another view of view projection, things like that. Render width is width of target. Tag is just, you can also put arbitrary object. View, how many viewport count on viewport indexes also, so that's how many slice of projection you have on renderer. So if you have 4 perspective or 4 look at on renderer, you'll have 4 viewport. Like viewport, what they call viewport, it's called viewport in the renderer way, is the sum of the max spread of, it should be view, projection, aspect, crop, and viewport. So it's the max, it's the spread count of that 5 pins exactly. So you have to implement this one, and you have to create one pin which outputs it. So you just output one instance of this validator, so it can be connected into the validator node, like the validator node except a validator type, so you output the validator instance. It's just standard C# plain type, no, there's no 4v anything, it's just really plain type. And well, you need to pass the spread of value as pins to be able to pass them around to the validator. So here I just, because like bonding sphere is not really known by 4v, I split it in center radius, so vector 3 float, and inside the sphere is set as the sphere is set as center radius. So, but with really little plugin, you can really start to affect the whole scene. So actually validator and layer are a bit less difficult because they don't manage much resources. Like all the other ones, they have to manage, you have to manage resource lifetime, that it needs to be created somewhere, that at some point it might not be used anymore, so you have to decide if you want to keep it when it's not in use anymore, or if you want to destroy it. So you have to, well, there's helpers, but it's still decisions that needs to be taken. Whereas layer and validator are a bit more, they are part of the render pipeline, but they don't really own resources. So this whole creation and destruction is just really much more streamlined. You don't have too much to do. So what the sphere does, it's really, like in the object settings, it's object about to be drawn. So it's draw call index, so it's internal slice index of the inside the shader. Geometry is what is the geometry instance. Geometry from layer, because you can assign geometry from downwards. So it will tell you if geometry comes from layer or comes from geometry pin. Iteration count and iteration index is if you use iteration inside. And render state tag is you can assign arbitrary object to render state, so you can also grab that. And world transform, which is transform in, which is quite important. So in that case, we get the world transform, we get the bounding box of geometry, and we transform the bounding box of the geometry. So just vector, it's transform coordinate. And then we have bounding sphere contents. And it will tell you contents if it's, you can also play a bit with those. So for example, if you say intersect, it will only grab, yeah, I don't need it. Hmm? Ah, yes. Oops, I forgot that one. Okay. Yeah, you can say only the ones that intersect purely. So you can say the containment feature gives you totally inside, or partly inside, partly outside. So you could even put containment as, you can put that as parameter, and you can say only the sphere, the box that are along the sphere, I want to draw them, all the other one I don't want them. So you can obviously do all the one outside, or if you want to do all the one inside, that will be contains, obviously. And if you want to say contains or intersect, you can, well, you can do or you can do different of this joint, which means they're completely independent, so they're both outside, and then you also include them. So you can really do small plugins to really control this fine-tuned rendering and build your own small condition. And yeah, when you start to have like really big, well, all big shader with light on every single attributes, well, obviously you start to get really big gain of doing it that way.
Is there any way to do this with instancing?
No, because instancing works by batch. So that means if you consider a layer, like in this case, like the whole pack of instances becomes one element. So it becomes one unit in that case. So one unit is the whole. You don't think into geometry as individual in slice. You think about one batch. So one slice is one batch of geometry. That means we'll need to combine all the bounding box from the batch to check, or for individual, we'll need to split which buffer, but we don't know which buffer is what. So those you have to do manually. They are good candidates for compute shader, by the way. I think there's a CA indirect append in the girl power, which does exactly that type of operation, but for instance geometry. So yeah, this one is more for the more design convenience. If you start to do heavy instancing, you need to go a bit more in the compute part, and it's a bit more difficult. Okay. But yeah, it's really easy to write the small function here with a template and apply any form of whatever functions needed. Like all the especially if you have a bit of interactive logic, as this object is selected, for example. So you have the get slice, remove slice. If it's selected, you just draw a sphere. If it's not selected, you draw something else. And you never have to worry about any select anymore. And the last one, I think, because we're perfect, almost done. Well, I think that's good timing, because that's, yeah, that's, well, there's mini too, so I'll go through them. And the other one is custom layer. I'll quickly show version of it. So idea is, oh, this one is still not gonna work. Well, idea is with layer, now layer has also a world. So that means so layer itself has a transform, so, which is not dependent on the camera. So that means you have view projection, but you also have this world layer node, which actually transforms a layer, and it replicates the layer. So you can, for example, say, oh, I want to really move all this, but you should not touch the camera, because if you touch the camera, you will affect all the shading. So if you apply this, if you move your layer, you use the view transformation. The problem is using the view transformation to move a layer will move the camera. If you move the camera, you move the half angle. If you move the half angle, you move the specular reflection. So you don't want to do that. So instead, you use the world transformation, which say move the whole objects along this transform, which is, well, extremely simple. It works. You have a world node, and you put a transformation. So I'll put a translate, transform, and you can spread the transform, and the world transform really replicates everything. So if you have a layer which draws like 100 boxes on one sphere, it will draw 100 boxes on one sphere on these two locations. So yeah, if you start to put 1,000 transform, but you have a lot of objects, it will multiply a lot. But so one of the funny thing is you can use all this, for example, integral transform. So when you do these self-multiplying matrices, so you can do this whole thing, but instead of doing self-multiplying matrices for only one box, if you look, I don't think this one has add-on pack. Oh, was that integral transform in the add-on pack ever? Is it in add-on pack? No. Okay, it really should be. So if you use it as a spread of transform, it's going to be quite difficult because here you have 100 boxes, so you need to multiply the 100 boxes manually again through, you need to do a select to make sure you replicate the layer transform 100 times and you multiply it 100 times to have this object translated 100 times and then 100 times in the other direction. So it adds a lot of logic, whereas if you do it at world level, instead you just put your spread of transform and it's just done for you. So that makes life much, much easier. And so yeah, you can do all the strange rotation and scaling. But no, instead of using world transform like this, idea is to use a quick custom layer plugin to do it instead. So that will do exactly the same thing. So instead it will build the integral transform inside. So you put only one transform, how many times you need it. It's like a repeater node, more or less. I don't know how it's called in some engine, repeater.
Ziel repeat is called in Werkzeug.
Huh?
Ziel repeat, they call it in Werkzeug.
Okay, so well, anyway, it's replicate or so this one has a transform on how many, so it will not need a spread of transform. It just grabs the initial one and how many times you want to repeat the transform to itself. And you have layer out here, and it does pretty much exactly the same, but it does it inside layer. So I'll go quick. So you have difference for layer. You have this interface you need to provide, which is called layer host. So you tell I am a layer, basically. You have to tell that, or you have to tell to the DX render graph, you have to manifest yourself. So you have to say, hey, hello, I'm here. You need to use me. If you don't put the interface, I don't know that you need to be rendered. So I need to put this. So you have a layer input and a layer output. And they have to be wrapped into a resource because they can be run in different devices. So they are not once per evaluate. They can be run 20 times. Like resource can be run once per screen, once per monitor. There are different customization. And layer can be rendered once per renderer. So it has even different frequency. But so that means you need to keep track still of which device has been assigned, which we'll see here. So on the evaluate, normally the layer is just a draw function. So you have to say, just register myself and update with a render context. Every render context that needs to render this layer will call update first. So that means this render context needs you. So in that case, we just say, if it's the first time, just create a new render and assign the render function, which is here. So you just give the render function. And the render function is the most interesting one. It's when every time a renderer calls render, you receive the context and the settings. So the standard pattern for every layer node is if it's disabled, it's just will accept group, I think. Yeah, group is a bit special because it does this. It doesn't draw if you disable, but normally other layer, they will so if you have like within projection, if you disable, it's not, you just pass through. So you just, it's like if the node did not exist. So it still renders, but without modifying the settings. So here you say, okay, you need to check if the input is connected. You take the repeat counter, and for each time you need to repeat, you get the initial transform and you multiply it with itself n times. And every time, for each iteration, you call render all, which says gets everything which is on top of this layer input, and call render on them, but with these new settings. So the only thing which needs to be taken care of is matrix needs, like, you need to restore after. So here you change the transform. So at the end, you need to set the transform back to the original value. So you need to, it's a bit like a stack. You need to push to the stack to say, no, I modified the layer, but you need to, it's like an undo. So you need to modify your layer, but then you still always need to undo. You need to not forget to, because otherwise the world transform will still be for the next one, and you don't, once you're done with your part, you should clean up, basically. And yeah, so yeah, you can create repeaters at layer level. So instead, same of building tons of integral spread repeat, you can just repeat the whole layer in one go. Or you can, this one is a good last example. It's like, for example, here we want to say, I want two viewports. When dealing with viewport, it's always a bit tricky sometimes. So, well, first, no, like the fact of having them in normalized was quite a big mistake, but I can't change it. I tend to really prefer to work with viewport in pixels because it just makes so much sense. So, like, ideas would be to say, okay, we want to replicate, to push this slice to, we want to push this one to this viewport and this one to this viewport, but we don't know how yet. So, idea is, in that case, you have a group, and now you have the slice from, so it's a small layer plugin which allows you to do this type of routing. So this type of routing are always quite painful to do by patch, whereas with quick plugin on routing, they are really quick, and the layer will always make sure you preserve everything up and you touch it as less as possible. So for example, we want to say, I want it to the second viewport too. But now obviously the slice from and slice to, like there's only one slice. When you have group, the layer becomes a super layer. So that means the group becomes one slice. So this one slice will be all of it. It's like everything. So for here, one slice is everything. All this random box is one slice of layer. And here, this sphere is one slice of layer. Now, if you start to group on top, this is the whole box plus sphere is one slice of this layer. So every time you will call render on that, you will call this whole thing. You just group. But now, instead of group, you also have a cons layer counterpart. So that means now if you have here, if you change the slice, you can't really say, I want slice number 1 to viewport number 1. You can't really assign this part to the viewport quite easily because everything is already one unit here. So instead, you can use also cons. And cons will actually preserve. So it's really two layers. So it's just a spread of layer. Simply use. So the first spread is the guru and the second spread is the guru on the sphere. But now that means, for example, you can do. Yeah, I removed the quad to draw, so it's not appearing anymore. But now you can suddenly say, I want to draw only the sphere, so you can draw only the boxes. So you can say, slice from, so I want to route, it's a slice-wise operation also. So it's like, it will say, okay, take slice 0 and use viewport 0, render. Take slice 0, take viewport 1, render. Take slice 0, so here it's actually drawing twice for that reason. It will say, take slice 0, take viewport 0, render everything. text slice 1 or 0 render, and if you change, you can change slice 1, so you can suddenly assign. But in that case, you need a cons version, because you still need to know which is which. And the code is also reasonably simple. So, because it looks like it's doing complicated thing, but the inside is not even, that's the cool thing about it is the inside is not that complicated. So you still have your layer host as before. You have your layer in, layer out, no big difference. You still need to go through that. And you have slice from, viewport from, so they're just index of int. And you have the viewport list of viewport which are here, and in pixel in that case. I use pixel unit. So if you want to make this viewport, move it around here, you move it here. And so, well, evaluate, update is exactly the same thing. Normally you have this destroy, but layer don't really own resource, so you don't care about destroy when you implement layer. When you implement buffer or texture, you really need to take care of that, but for layer, they're a bit simplified on that aspect because they don't have any of that management to do. And so the idea is here, instead of rendering all a layer, now you can also decide. So instead of render all, you will have to say which slice you want to render. So render all will say take the whole spread of layer and render them one by one. Here you have to make the loop yourself and say, okay, I want to use this layer slice. So that will be that's a get slice on that layer, basically. Then you have a get slice on the viewport. So that's the slice of the viewport you want to use, and it gets slice this viewport. Then on then you need to, in the context, you need to assign the viewport. So you can either do it low level, but you have a bit of high level. Like the context has a render target stack. So when you push a texture to say I want to write to it, it will automatically, you can say push targets and viewports. Actually, if you don't push viewport, it creates a viewport for you. So it tries to do a bit of glue for yourself. So you can either set viewport low level, or you can say render stack, use the existing texture, but I want to change the viewport. So you say push viewport. So that means you say now you're only rendering to that viewport instead. So with only rendering at origin 35259, 3528, and a rectangle of 259 pixel by 161 pixel. And now we say we want to only render this one specific slice instead of the whole scene. So one specific slice will be either the box or the sphere. And once we're done, as said, we pushed the viewport, but we need to pop, so we restore the previous state. Otherwise, the viewport will still be attached. So every new, if I show it again, because it's not here. I'll do another group here. Yeah, actually the quad was representing viewport. Okay, let's show it with the group anyway. Yeah, the quad represents exactly a viewport because it's a full screen quad. But because now we have a different viewport, the full screen is not the full screen anymore. The full screen is the viewport is a rectangle. You never render to you always render to a viewport. So by default, the viewport is set to the texture, but you always render to an area of the texture. The fact that it's the whole texture is a specific case of it, which is the most common, of course, but it's still a specific case in the pipeline. So once you're done with the viewport, if you don't pop, actually, let's not pop it, you will see if I do something. It will probably complain, actually. Yeah, like actually the TTY will be not happy. So it will clean up your mess, but at the end of the frame. So that means anything that happens after you forgot to restore and the end of the frame, well, I have no idea. Let's call it undefined. And yeah, if you, well, it will be reason. Actually, you can even see it now. It's not very visible with axis and grid, but let's put a quad again. The DirectX11 layer. And I probably need depth stencil off. Yeah, you can see the quad actually. And let's put it full screen. And within projection. Yeah, you can see now I'm supposed to be done with my viewport routing, but I forgot to restore, so that means the viewport is still here. So that means anything which is here within projection is now assigned to the viewport because it's not being restored. So yeah, please restore. And there's only one small issue with dynamic and DirectX11. There's still this small issue. So when you recompile, you still need to re-double click the node. It's yeah, it's quite really nasty to fix. I hope I'll do that one of those days. But on dynamic, it's really quite tricky. So yeah, that's one of the things. You need to just double click the node again, or control right, I think. But yeah, now it's restored. Obviously, now it's restored. We are using the proper texture again. So yeah, all those things will be really difficult, but they can really easily be done when it's inside plugin. So I quite encourage to look a bit into it. Like, it can solve a lot of problems which are really painful otherwise. So, well, I think that's end of the workshop. So thanks for attending. I hope it was bearable.